Hello, in this video I'm going to discuss line integrals with respect to arc length. These are slightly different from the line integrals we discussed in the previous video when we were integrating differential forms over a given curve. The motivation for introducing these line integrals with respect to arc length is that sometimes we want to find the length of a given curve. And so how would we do this by doing a line integral? Suppose we have a curve, well, as is shown here on the left-hand side. In order to find the length of the curve, one method we could use is divide the curve up into small sections of length delta s, approximate the lengths of each of those sections, and then add all those up. And then when we take the lengths of the sections to 0, the approximations get better and better. And by adding those up, we obtain the arc length of the curve. And when the delta s's go to 0, this turns into an integral over the curve with respect to arc length. And we write the ds for this integral with respect to arc length. And so what should we use for ds here? Well, this comes from approximating small sections of the curve just by using the Pythagorean theorem. So if we have a small section of the curve, delta s, this is approximately a triangle, not exactly if it's a curve and not a straight line. And so the delta x is approximately the square root of delta x squared plus delta y squared. And this is what we use in order to say what is ds when we look at an integral with respect to arc length. So this integral over the curve, ds, is the square root of dx squared plus dy squared. So this is kind of just a notation that helps us remember how we compute this ds when we're actually doing integrals. And I'll explain what it means in the next slide. You may be able to guess what it means simply by the notation. But the length of the curve c, then, for example, this curve shown here, is going to be the integral over c. You have to parameterize c, as in the case of line integrals of differential forms, of this form square root of dx squared plus dy squared. Okay, so how do we evaluate this? So as I said, this square root of dx squared plus dy squared is kind of just a notation that suggests to us what we should be doing. And so let's discuss how we would actually evaluate it. So you need to parameterize the curve. And let's first suppose we can parameterize by x, the x coordinate, as in some of the examples we looked at in the previous video. If we can parameterize by s, the curve has the form y equals some function of x. Then, well, dx will just remain as dx. That will be the parameter that we use. And then dy, as in the previous video, is dy dx. And so if we formally plug in dy dx times dx for dx and then factor out the dx, we get that this arc length form ds is the square root of 1 plus dy dx squared times dx. And this is what we use for the arc length. We integrate over the curve this form, square root of 1 plus y prime squared dx. Okay, let's look at an example and do this in a particular case. So we'll find the arc length of this curve, which is given. We can use x as the parameter here because it has the form y equals a function of x. In this case, y equals x to the 3/2, where x goes between 0 and 1. All right, so the curve is shown there. And we can use x as the parameter. So parameterize using x. Then what we have is y equals x to the 3/2. This is the equation that's defining the curve, and the parameter x goes in between 0 and 1 along this curve. So x starts out at 0, we're here at the left-hand side, and then as x goes up to 1, we go along the curve up to the top here. So we need to know what dy is. Dy is just like in the other case when we were doing differential forms, is 3/2 x to the 1/2. That's the derivative of x to the 3/2 dx. So this is y prime dx, or dy dx dx. Okay, in order to find the length of this curve, we integrate with respect to arc length over this curve. So integrate, x goes from 0 to 1 in this parameterization. Actually, sorry, let me write the line integral without the limits first. So we do the line integral over this curve C of ds. And so when we convert this to a single integral, x goes from 0 to 1 in this parameterization. And then ds is a square root of dx squared plus dy squared. Then dy is 3/2 x to the 1/2, so we put that in for dy here. And so we have 3/2 x to the 1/2 squared will be 9/4 x dx squared. And then you think of factoring the dx out of this, and we just have this square root times ds, and that's the integral we need to do. Now, the integral from 0 to 1 of the square root 1 plus 9/4 x dx. So now we can do this integral. You can do a substitution if you like. U equals 1 plus 9/4 x. And when you do that, let's see, we get 2/3 1 plus 9/4 x to the 3/2. Then we also need to multiply by 4/9 to counteract this 9/4, which is here. So 4/9. And this is the indefinite integral. And multiply these 2/3 by this 4/9, we get 8/27. And we evaluate at the two limits. So at limit 1, we get 1 plus 9/4, that's 13/4 to the 3/2. And then when we evaluate at 0, we get 1 plus 0, so just 1 to the 3/2, which is 1. Okay, so this is the arc length of this curve. You can put it into your calculator if you like, in order to get a decimal approximation for this. Is approximately 1.44, the length of this curve, which is shown here. And we've done it by doing this integral, line integral with respect to the arc length ds. Okay, so this is one example using a line integral to calculate the length of a curve. So in the previous slides and in the example I just did, we were able to parameterize the curve using x as a parameter. But not all curves can be parameterized using x. So what if you can't write the curve in the form y is a function of x, y equals f of x? Well, the next case that you might consider is when x is a function of y. Then we have ds squared, dx squared plus dy squared here. And we simply replace the dx by dx dy times dy and factor out the dy. And so get that the arc length is the integral over the curve C with respect to the arc length ds. And the ds becomes the square root of 1 plus x prime squared dy. We take the square root of this formally, then this is what we get. Even more generally, we could say, what if we can't parameterize by y either? We can introduce some other parameter t, similar to when I discussed line integrals of differential forms, and get that the arc length is still the integral over c ds. So the basic formula for the arc length still remains the same. And then you simply plug in x prime of t dt for dx and y prime of t dt for dy. Really, it's like the previous case with the differential forms. And get that the ds becomes the square root of x prime squared plus y prime squared dt. Here this x prime, or x dot, is the derivative of x with respect to t. So we can do these integrals with respect to arc length as long as we've parameterized the curve. We just have to know how to calculate ds, the arc length form. Okay, I'm going to do another example. I'm going to now integrate a function with respect to arc length. And this is not too complicated, not too different from just finding the arc length. The difference is that we just put 4x in as the integrand. So we want to integrate over a curve which is given. In this case, the curve is a parabola, or a segment of a parabola. 4x ds. This ds is going to be determined by the parameterization in the way that we have been discussing. And the curve here is a segment of the parabola between 0, 0, and 1, 1. So see this curve. And the curve is y equals x squared. Okay. Well, we can grind through and calculate this, but I would also like to describe what this line integral of this function with respect to arc length would represent. And I'm going to try to do that by drawing a diagram here. So we have this curve C in the xy plane. And then the function 4x we could think of as being the height above this curve. Then this line integral represents the surface area of the surface, which is described by the height above this curve given by 4s, and then along this curve. So it's a surface area, which I'm going to try to draw. So let's draw our three-dimensional axes. So our x, y, and z axes. And this will be 1 on the x-axis, 1 on the y-axis. And this is the point 1, 1, 1, 0. So x coordinate and y coordinate 1 and z coordinate 0. And then this parabola, segment of the parabola in the xy plane, is a curve in the xy plane, which goes from 0, 0 to this point, 1, 1. This curve, the parabola when we look straight down on it from along the z-axis. And then 4x here, think of as being the height above the xy plane along this curve. So we have 4. Obviously the scale on the z-axis is different than on the xy axis because we need to fit in 4. So is up to 4 here. And the surface that we're getting the surface area of when we do this integral is this curved surface with height above the curve y equal x squared given by 4x. And so it might look like this. So we're thinking that this is a curved surface which is going straight up above the curve y equals x squared, and its height at each point is 4x. So at the end here it's 4 because here x equals 1. So this is 4. So if we take one little segment of this, say this little segment with length delta s, the height here is going to be approximately 4x. So if we take a given point along the curve, it's going to be height 4x. And so this part of the surface has area approximately given by delta s times 4x, its height. So say that this little part is delta a, or it has area delta a, and that area is approximately delta s, the arc length at the bottom, times the height 4x. And so when we do this line integral with respect to arc length, we have this height times this ds, delta s becomes ds, and we get this area of this curved surface. Okay, so this is a physical interpretation of what this line integral is giving us. A surface area of a curved surface. Okay, well, but we can still just continue to evaluate this integral without really thinking about this interpretation if we want. So let's now just evaluate the integral. So we can parameterize using the x coordinate as a parameter. So parameterize using x, and we have y equals x squared, and x goes from 0 to 1, or 0 to 1 if you like in the three-dimensional diagram. And dy is 2x dx. Right, so we put all that information into the line integral. Line integral over c of 4x ds equal to the integral. X goes from 0 to 1 when we parameterize using x, so the integral from 0 to 1 of 4x times the square root of dx squared plus dy squared, but dy is 2x dx, so 2x dx squared. All right, and then we'll factor out the dx squared in from the square root. And the integral, the single integral we need to calculate is this integral from 0 to 1 of 4x square root of 1 plus 4x squared dx. Right, and once again, we can do this integral. We'll find the indefinite integral by doing a substitution. U equals 1 plus 4x squared. And when you do that, you get the indefinite integral is going to be 1 plus 4x squared to the 3/2. And we would need to divide by 3 in order to counteract the 3 in the exponent there. So 1/3, 1 plus 4x squared raised to the 3/2 power. Okay, and so now it's just a matter of plugging in the limits. So it would be 1/3 times, plug in 1 for x, 1 plus 4 is 5, so 5 to the 3/2. And when we plug in 0 to x, we just get 1. So this would be the area, this curved surface. And once again, if we wanted to put this into our calculator, we get this is approximately 3.393. We want a decimal approximation. Okay, so another example of doing a line integral with respect to arc length. I'm going to do one more example. It's kind of an application, and that's calculating the mass of a wire with varying density along the wire. And the density here is going to be the linear density. When we were talking about double integrals, I talked about doing finding the mass of a plate, and the density was the surface density, mass per unit area. And here the density is the linear density, mass per unit length. And so we have a thin wire, and the two dimensions that are perpendicular to the direction of the wire are simply disregarded, and we just think of the density per unit length. And so in order to calculate the total mass of the wire, we cut it up into small little sections, which are now each of length delta s, and calculate the mass of each of those sections, and then add all those up. And when we take the limit of the length of the small sections, the delta s goes to 0, that becomes a line integral with respect to arc length. Okay, so here's the situation. In this example, we have this wire and its shape is part of a sine curve from 0 to pi over 2, and this part of the sine curve is where sine is going up, and it looks like this approximately, and this curve is given by y equals sine of x, and the density of the wire, the linear density, is rho equals sine of 2x. And so if we consider what is the mass of a small segment here, say that's delta m, the mass of a small segment, that's going to be the length of that segment, delta s, times the density, which is the mass per unit length. So delta s times rho. And so in order to get the mass of the entire wire, we add up the masses of all the individual sections, and that becomes a line integral with respect to arc length. The integral over this curve is called C, as we seem to always be calling curves. The integral over this curve of the density times ds. So rho ds. Okay, and so we can parameterize this curve by the x-coordinate yet again. So parameterize using x. X is the parameter, and y is sine of x. And x goes from 0 to pi over 2 as we move along this curve. Dy is cosine of x dx. Okay. So now we have all the information we need to put in order to convert this line integral to a single integral. We have the integral, x goes from 0 to pi over 2, of the density rho. The density is sine of 2x. And ds is square root of dx squared plus dy squared, which is going to be cosine x dx squared. All right, as in the previous example, factor out the dx, and we just get a regular integral that we will evaluate. When we factor out the ds, is 1 plus cosine squared of x dx. All right, this is now an integral of a single variable, the standard integral, and we know how to evaluate it. And again, as in the previous examples in this video, we can use u substitution with u equal what's inside the square root. So u equals 1 plus cosine squared in this case. And when we do that, the indefinite integral is 1 plus cosine squared of x to the 3 halves. And we need to divide by 3 in order to counteract the 3 in the exponent here. And this is evaluated from 0 to pi over 2. When I first wrote this down, I also forgot that we have to counteract the 2 here. When we differentiate cosine squared, we get negative 2 cosine times sine, which is negative sine of 2x. So we need a negative sign actually and a 2 in order to counteract the 1/2 in the exponent. Okay, so this is the indefinite integral. And now we just evaluate at the limits. So we have negative 2/3. We evaluate at pi over 2. Cosine of pi over 2 is 0, so we just get 1. And then when we evaluate it at x equals 0, cosine of 0 is 1, so we get 2 to the 3 halves. And so the total mass would be 2/3 times 2 to the 3 halves minus 1. Okay, this is the last example I'm going to do about line integrals with respect to arc length. There are more examples in the exercises and also the follow-up quiz. A few general comments about line integrals, both of the types, before we move on to the next topic. So line integrals are sometimes called path or contour integrals. These are just different words for the same thing. And they arise in many applications. I've sort of gone over a few as we went through. Really, the main application, particularly for line integrals of differential forms, is calculating the work done. And we're going to come back to this, as I said in the last video, in a future section. Another possible application is finding the flux of fluid or an electric field between one region and another region in the plane. And so if you have a fluid flowing in 2 dimensions, the amount of fluid that's flowing through a given curve could be given by a line integral with respect to a differential form. And line integrals are also connected in a certain way to double integrals, which is going to be the next topic cover in the next video, which is about Green's theorem. Green's theorem gives us the connection between double integrals and line integrals.